3. Assalamu alaikum. I'm Omar Mansour, and we are going to introduce our group project. Our group number is 5. The subject is fluid mechanics, and our topic for this project is wind turbines. This is the group members. I am Omar Mansour, and my matric number is 209416.
My name is Maran Mohammed Magdi, matric number 208650.
My name is Guo Jiaqing. My matric number is 208938.
This is our content for our project. At first, we will talk about the introduction. Secondly, we will move on to the lecturing findings, and then concept of the system. After that, result and discussion, then recommendation for improvement, and after that,
Okay, for introduction, first, the boundary layer. What is the boundary layer? It is a layer of fluid in the immediate vicinity of a boundary surface, where the effect of viscosity are significant. The liquid or gas in the boundary layer tend to clipping to the surface. The boundary layer includes the laminar boundary layer and turbulent boundary layer. The laminar boundary layer is very smooth flow. It creates less friction drag than the turbulent flow, but is less stable. Boundary layer flow over a wind surface begins as a smooth laminar flow. As the flow continues back from the leading gauge, the laminar boundary layer increasing in the thickness, and it becomes the turbulent boundary layer. And next, the drag and lift. Lift is a component of the force that is perpendicular to the coming flow direction. It contrasts with the drag force, which is a component of force parallel to the flow direction. Lift acts in an upward direction in order to counter the force of gravity. Okay, next.
For the literate finding. The biggest challenge in the world is producing energy. Thermal power facilities based on coal, diesel, which lead to environmental degradation, meet nearly all energy requirements in order to prevent this harmful electricity. Other energy options, such as solar, wind, and so on, must be used. However, wind power is regarded as a safe domestic energy resource based on a variety of research, like what National Research Council has done in Washington, D.C., and how their research was talking about the wind and the wind turbine, but not much about the airflow. Another good research from German University in Cairo, Egypt, which explained clearly the airflow that acts and rotates the wind turbines and how the best profile at each wind speed can be selected according to the maximum sliding ratio. Also, the angle of rotation wings about itself is based on the air speed to get the best result. Our current work is highlighting the fluid mechanics based on both the fluid mechanics design side of these wind turbines and how can good design generate electricity from the flowing of air.
Okay, so the most important thing in our research was wanting to focus on efficiency as much as possible. And we discovered certain shapes that are more efficient than the other. So we wanted to, in this review, we wanted to go into the current state of the art for wind turbine blade design is presented, including theoretical maximum efficiency, propulsion, practical efficiency, especially horizontal axis wind turbine blade design and blade loads. In this presentation, it will provide a complete picture of wind turbine blade design for our prototype, and it shows the dominance of modern turbines, almost exclusive use of horizontal axis rotors. The aerodynamic design principle for a modern wind turbine blade is detailed, including blade plane shape, quantity, aerofoil selection, and optimal attack angle. Next slide. So we discussed a lot. We had different conceptual designs, including four-bladed turbine, which we'll talk about later, and other practical inefficiencies and the redirection of air over the aerofoil, and choosing which axis to use. We had the vertical axis turbine, but it would be hardly be able to beat the efficiency of a propelled type turbine like horizontal axis, because it just has low yield. And they can work with winds blowing from each direction, but horizontal axis, there's a yaw motor which turns the nacelle towards the wind direction. Next. So here in our CFD analysis, we had a lot of inefficiencies as well. But if we're gonna look for the core dimensioning, the quantity of blades is considered negligible in terms of efficiency. But however, in practice, when blade losses are considered, a 3% loss, it is incurred for two-bladed design, and a 7% to 13% loss for one-bladed design when compared to something like a three-bladed design. But someone might just ask, why don't we do like a four-bladed design? It in fact offers marginal efficiency. It increases, but it does not justify the manufacturing costs of an extra blade. What we could have done better is we could have made the base a lot more smoother, and it would also help with the structural stability. But we also notice for our simulation, we had a lot of our normal parameters for the velocity and the thermodynamic parameters, the turbulence parameters. They were both normal at sea level, with wind blowing to the direction of the wind turbine at 5 meters per second. And the noticeable thing is that the wind also blew in the other direction, here as shown as -1%, and to the maximum to 11 meters per second to facing the wind turbine. And this kind of energy dissipates, and the rest is turned into electric energy, which proved somewhat efficient. Thank you. Next slide.
Okay, for conclusion, the horizontally mounted three-blade design with yarn and pitch for its capacity to survive and operate under various wind conditions dominates the modern wind turbine industry for reasons of efficiency, control, noise, and aesthetics. This design, which is now the industry leader and will remain so for the foreseeable future, have spanned an international supply chain. In other words, there is a huge demand for it, and it will stay for foreseen time. That's all. Thank you.